Okay, let's unpack this. For the longest time, when we talked about the AI revolution, we were really focused on generative AI.
Right. The large language models,
Yeah.
the ones that could write a poem or, generate an image if you asked it to.
Exactly. It was all about creation. But the game has fundamentally changed, and it's accelerating much, much faster than most people realize.
That's because we've moved beyond just creation and into execution. We are now witnessing a transition to something far more autonomous and, frankly, impactful: agentic AI.
So this isn't just about making the AI talk anymore.
No, not at all. It's about making it decide, plan, and then execute these really complex sequences of tasks, and to do it without requiring constant human monitoring or prompting.
That's the key distinction, right? The difference between a tool that you use and, well, a coworker that works alongside you.
That's a great way to put it.
But this shift from a chatbot to a true autonomous agent, I mean, that doesn't happen magically. It must put immense stress on every single part of the technological stack.
Oh, absolutely. The challenge has moved from just, tweaking an algorithm to fundamentally solving core engineering and, in some cases, physics constraints.
So we're talking about massive, radical changes across the board.
Precisely. It demands changes across 4 intertwined layers: the algorithms that govern memory, the actual software architecture that allows these agents to coordinate, the physical memory chips themselves that power the data centers.
And then, of course, how we as humans interact with and regulate these autonomous systems.
Exactly. All 4 have to evolve together.
And that is our mission for this deep dive. We're going to give you a complete shortcut to understanding the foundation of this agentic future.
We'll start with the software, then go deep on the hardware, and then talk about the impact.
Right. We'll look at the new software blueprints governing these autonomous agents, then dive into the really unexpected hardware revolution happening right now in memory and storage.
And then we'll wrap up by exploring the critical impacts this tech is already having on the future of work and, maybe even our own cognitive abilities.
So to start with a clear definition, what exactly is an AI agent?
Okay, so an AI agent is an autonomous system that perceives its context, it reasons about its goals, and it takes actions to accomplish them.
It's an integrated system, then.
It is. It combines a reasoning engine, which is the LLM, with memory, which is often handled by vector databases. Then it needs the capacity to use external tools and APIs.
And critically, the orchestration frameworks that tie it all together.
That's the linchpin. Without all 4 of those components working seamlessly, you just have a powerful but ultimately stateless chatbot.
So let's start at the top of that stack in the coding layer. We have this fascinating analysis of 542 real-world agent development projects.
And this is great because it gives us insight not into what researchers think will happen, but what engineers are actually building right now.
So what's the foundational language they're using? Is it still Python?
Oh, absolutely. The foundational language for innovation is still predictably Python. It is the absolute backbone, showing up in 52% of the projects that were analyzed.
And that's not really a surprise.
Not at all, given the deep established ecosystem it has. I mean, tools like TensorFlow, PyTorch, and the foundational agent frameworks like LangChain. They all live in the Python world.
So it still dominates the prototyping and data science side of the stack.
It does. But, and this is a huge but, when you look at how companies actually deploy these systems in the real world, that single language approach breaks down immediately.
Because production demands speed, resilience, concurrency, things Python isn't always famous for.
That's the reality check. When you move beyond the lab and put agents into mission-critical business processes, you need what we call a polyglot stack.
A polyglot stack, so multiple languages working together.
Exactly. Python is used for the core logic, but it has to be paired with faster, more efficient back-end languages to handle all the real-time demands.
Like what? What are they pairing it with?
Well, Node.js showed up in 17% of projects, and Go was in 12%. These are essential for building scalable, real-time APIs that can manage the massive data flow an agent needs when it's interacting with, say, a live business system.
Okay, and what about the actual user interface, the part that people see?
Right, on the client side. So where the agent's output needs to be embedded into a web interface or a corporate dashboard, you're seeing JavaScript in about 10% of projects and TypeScript in 6%.
And those languages make sure the user interaction is fluid and, doesn't feel slow.
Exactly. Low latency is key.
So the big implication here for any executive or manager listening, the days of hiring a lone AI guru are just over.
Completely over. This level of agent development requires a diverse team. It absolutely signals that AI has left the isolated research lab and is now becoming core IT infrastructure.
So you need your Python data scientists, but you also desperately need other specialists.
You do. You need skilled back-end engineers who can handle the speed and scalability of Go and Node.js, and you need specialized DevOps teams to manage the deployment of this really complex multi-language system.
And I imagine the integration points between these different languages are now the new weak spots.
That's where things fail. Those are the new points of failure for enterprise AI systems.
Okay, so if Python is the language, the orchestration frameworks are like the nervous system, connecting the brain to the muscles.
That's a perfect analogy. We've moved from figuring out how to write one good prompt to figuring out how to coordinate an entire system of components.
And LangChain is still the king here, right? The
Yeah.
glue connecting all the pieces.
It is. It remains the gold standard, used in a whopping 55.6% of projects. It connects the LLM to the vector databases and all the external tools.
But there are new players emerging.
There are, and what's truly fascinating is the emergence of frameworks designed explicitly for multi-agent collaboration.
Multi-agent. So agents working together.
Exactly. These agents aren't working in isolation. They're working like a swarm of microservices, all coordinating on a single goal.
That sounds incredibly complex. Why do you need a team of agents instead of just one super agent?
Because specialized labor is more efficient, just like with humans. Imagine a complex task, like analyzing a new market entry strategy. You could have one agent that's dedicated entirely to data retrieval. It uses something like Llama index, which was in about 7% of projects, to efficiently query all your internal sales reports.
So that's the research agent.
Right. Then you can have a second agent that's just dedicated to reasoning and synthesizing the findings from that data. A third agent might be the editor agent, refining the final output for tone and clarity.
And maybe a fourth agent is responsible for executing API calls, like booking a follow-up meeting with the human managers.
You've got it. You are modularizing the cognitive process itself.
And as soon as you do that, you introduce massive governance concerns. I mean, if Agent A hands off to Agent B, who is responsible if the final output is wrong?
The governance takeaway is paramount, and it requires executive attention. These orchestration frameworks are not just experimental libraries anymore. They have to be treated as mission-critical infrastructure.
Because they're making decisions that could impact revenue or compliance.
Exactly. So you must have robust control, observability, and most importantly, auditability. You need to be able to track precisely why Agent A decided to hand the task to Agent B, what data it used, and what guardrails were in place.
You need a clear paper trail, even if it's all digital.
You do. It requires embedding logging and validation at every single stage of the agent's loop.
Okay, so let's move to the actual intelligence, the large language model itself. Unsurprisingly, OpenAI still sets the benchmark.
It does. It remains the default brain for most applications, used in just a huge 73.6% of projects.
That market share reflects the current capability, sure, but what are serious enterprise projects doing? Are they really locking themselves into a single vendor?
No, they're not. And that reflects what we call a true multi-cloud mindset. They are deliberately avoiding reliance on a single vendor to balance capability, cost, and those crucial compliance concerns.
So what does that diversification look like in practice? Who's the number two?
Claude is carving out a really strong 16.6% share. It's frequently favored by enterprises that prioritize safety and alignment.
Especially if they're dealing with sensitive data, like medical or financial records.
Exactly. They believe Claude offers more robust protections against undesirable outputs or hallucinations, which just makes it a lower-risk choice for those high-stakes interactions.
And what about the others, Google and Meta?
Google's Gemini is seeing adoption at around 3.9%, and Meta's open-source Llama is at about 2.8%.
Llama's role is interesting because it's open source.
It is, and it's often employed for cost-efficient batch tasks, things that don't need real-time, cutting-edge intelligence, but require high throughput at a predictable lower cost.
And because it's open source, you have maximum control over fine-tuning and deployment.
Which is critical for companies focused on strict data residency laws.
So executives have to manage an entire ecosystem of AIs, not just pick one.
That's the key takeaway here. The need for LLM vendor agility. Your systems must be architected so that you can swap out models seamlessly.
So you could use OpenAI for general reasoning, Claude for safety-critical tasks, and Llama for batch processing.
Without having to rip up your entire orchestration workflow. It means your procurement and risk management teams need to be fully aligned with this multi-model reality.
Okay, so if the LLM is the brain, memory is what makes the agent truly functional.
Right. Memory elevates it beyond just a temporary interaction. What separates a useful, persistent agent from a chatbot that forgets everything you said 5 minutes ago is its long-term recall.
And memory has become the new competitive battleground in AI architecture.
Absolutely. It's handled primarily through vector databases. These allow the agent to encode, store, and quickly retrieve context, past actions, user preferences, everything really.
Looking at the market, who's leading the pack?
Among the managed services, the leader is Pinecone. It's acting as the centralized cloud of recall in 22.6% of projects.
That's the managed cloud-native option. What about open source for teams that want more control?
Open source solutions are critical for that reason. For data residency and cost control, V8 accounted for 16.5% of projects, and we're seeing strong adaptation from established systems too.
What do you mean by that?
Crucially, Postgres with the pgvector extension appeared in 18.8% of projects. This is a massive trend.
So enterprises don't have to throw out their entire database infrastructure.
Exactly. They can leverage their existing trusted SQL databases to store structured data right alongside unstructured vector data. That saves an incredible amount of time and money, and it preserves historical IT trust.
But integrating all this memory, especially across different data types and vendors, must introduce some serious new risks.
Oh, it introduces new, complex risks that absolutely warrant board-level discussion. Beyond the obvious concerns like data residency and cost predictability, the most insidious technical challenge is something called model data drift.
Model data drift, what exactly is that?
Okay, think of it this way. When you embed data into a vector database, the LLM uses a specific embedding model to translate that data into a mathematical vector. That's the memory.
Right.
But if you later upgrade or swap out your core LLM, your reasoning engine, or its embedding model, the new model might interpret that data completely differently.
Oh, so it renders all your old stored memories irrelevant.
Or just inaccurate. You essentially have to re-index or re-encode your entire knowledge base, which is an immensely costly and time-consuming process.
Yeah.
Managing and mitigating that drift is now a core operational challenge for anyone running these systems at scale.
Wow. Okay, let's talk about the two final trends shaping the software stack: access and interface. First, the democratization of all this.
Right. The sources show that nearly half of all projects analyzed, 247 out of 542, are using no-code or low-code tools.
That's a staggering number.
It is. Tools like N8N, Zapier, and Make are making powerful multi-step agent creation accessible to business users, not just trained engineers. This is rapidly accelerating adoption and experimentation.
And while that accelerates adoption, it sounds like a governance nightmare waiting to happen.
It absolutely is. Rapid low-code experimentation is great for innovation, but if it's not governed, you quickly face massive IT fragmentation. Businesses need clear integration standards, robust security policies.
And strict auditing on what data these low-code agents are allowed to access and move.
Otherwise, the shadow IT risk just explodes.
Okay, and on the interface side, we are clearly moving past just typing text into a box.
Yes. Voice is quickly becoming the new interface, what some are calling the interface of trust, particularly for high-stakes customer interactions.
How many projects were focused on voice?
181 projects specifically mentioned integrating voice, speech, or audio components. The huge challenge here is latency. Human conversation is rapid. It requires split-second response times.
So what tools are they using for that?
Tools like Twilio handle the telephony and the routing, while specialized conversation engines like Vopi and Retel manage that really low-latency interaction necessary for real-time speech.
And for the actual voice generation and recognition? The part that sounds human.
For transcription, OpenAI's Whisper is doing a lot of the heavy lifting. And on the generation side, 11 Labs has really set the benchmark for lifelike synthetic voices, which is crucial for maintaining user trust in these systems.
Okay, that gives us a really comprehensive picture of the complex multi-agent software architecture. Now let's go deeper to the hardware that has to support all this extreme demand.
This is where it gets really interesting.
I was just about to say that. The explosive growth in agentic AI isn't just a software story. It's driving a profound engineering and, well, a physics challenge in the data center.
It is. The massive, unprecedented demand for data bandwidth and storage capacity is forcing a revolution in the silicon that few people outside the semiconductor world truly appreciate.
So what's the central conflict here?
The central conflict in AI today is hitting the memory wall. Bandwidth and capacity demands are just growing exponentially to feed these massive models.
But the existing system architecture is constrained by two physical factors.
Right. Latency is limited by the speed of light and electricity. And power consumption of existing systems has basically reached its saturation point.
Mm-hmm.
We simply can't keep pouring more power into chips without them overheating or the entire data center becoming unsustainable.
So we need to move data faster and process it closer to where it's stored. What's the primary tool for the bandwidth challenge inside the server?
That would be high bandwidth memory,
Hmm.
or HBM.
Right.
HBM stacks multiple memory chips vertically and integrates them extremely close to the GPU. This provides incredibly short data pathways. It's absolutely required in AI servers for training and running these huge models.
But as you pointed out, increasing bandwidth so dramatically increases power consumption and heat.
It does. HBM requires immense thermal management solutions because the heat generated is just intense. That's a huge issue.
Hmm.
But if HBM solves the bandwidth problem, what about the capacity problem? GPUs have physical limits on how much HBM they can actually hold.
And that's where Compute Express Link, or CXL, comes in. It lets memory scale beyond the CPU.
CXL is the fundamental game changer for capacity. It's an industry-standard interface that lets CPUs, GPUs, and memory all talk to each other extremely fast. And memory expanders using CXL are now emerging.
You mean CXL memory pooling?
Exactly. This allows system builders to create these massive, scalable memory spaces that are completely independent of the CPU's physical capacity limits.
Wait, can you explain what memory pooling functionally means for a data center?
It means elasticity. So traditionally, if you had a server with 1 terabyte of RAM, that 1 terabyte was locked to that specific CPU, even if the workload only needed, say, half of it.
Right, so a lot of it was just sitting there wasted.
Wasted. With CXL memory pooling, you can decouple the memory. A large rack of memory can be dynamically shared or pooled across multiple CPUs and GPUs as needed.
So you're increasing hardware utilization and lowering cost.
Fundamentally, it reduces wasted resources and significantly lowers the overall cost of running these large models that might need huge amounts of memory sometimes, but not all the time.
Let's focus back on HBM for a second, because that thermal management sounds like an engineering nightmare that just needs continuous breakthroughs.
It is a continuous battle against physics.
Hmm.
HBM4, the latest standard, has had to adopt cutting-edge and very expensive logic processes just to achieve significant improvements in energy efficiency.
Because if they didn't, the power consumption would just keep climbing exponentially.
And the chips would throttle their performance because of the heat. It would be self-defeating.
I saw a major change mentioned in the sources about how the chips are physically stacked to improve that thermal performance. The transition from TCB to HCD. Can you break down why that's so pivotal?
This is a classic example of solving an engineering problem at the physical layer. So traditional manufacturing uses thermal compression bonding, or TCB.
Okay.
TCB requires physical bonds and uses an insulating gap material between each stacked chip die. This gap material, while necessary, limits how many dies you can stack, and, critically, it increases the thermal resistance. It makes it harder for the heat to escape.
So the stack gets hotter, and you literally can't build it any taller.
Precisely. Now, Samsung is leading the transition to something called hybrid copper bonding, HCD. HCD enables a direct interconnection between the chip layers.
So it gets rid of that gap material.
By eliminating that gap material, you solve multiple problems at once. You can stack a higher number of dies, which increases capacity, and most critically, the thermal resistance is significantly reduced because heat is conducted much more efficiently out of the stack.
That's a fundamental leap.
It is. It directly addresses the thermal and capacity limits imposed by high bandwidth.
And beyond just efficiency, there's a move toward customization.
Yes, the complexity of AI workloads, from huge training runs to specialized inference tasks, means a one-size-fits-all chip just doesn't work anymore.
So suppliers are moving toward custom HBM.
They are. By using advanced logic processes, they can secure about 25% of additional gray area on the standard base die. This space is then used to integrate customized features, like a memory controller optimized for a specific network, tailoring the solution to each customer's demanding needs.
Okay, so HBM is crucial for GPUs, but the broader server market still relies on conventional memory like DDR5.
Which is reaching incredible speeds, up to 8,000 MTs. But the most unexpected development, the real market shock, is coming from a type of memory traditionally confined to mobile devices. LPDDR5X.
This is the truly disruptive seismic shift in the supply chain.
It is. LPDDR stands for low-power double data rate. Historically, it was only in cell phones and tablets because its primary goal was superior power efficiency.
It operates at a really low voltage.
Ultra low, 0.5 to 0.6 volts, which is significantly less than the 1.1 volts needed by server-grade DDR5. It consumes about 20% less power than its predecessors while still hitting remarkable speeds.
So high speed and dramatically lower power consumption. But why did a memory chip designed for a cell phone suddenly become critical for the data center?
One reason, the NVIDIA factor. NVIDIA recognized that at the scale of a hyperscale data center, power consumption is the ultimate limiting constraint, both for cost and for cooling.
So they're strategically using LPDDR5X in some of their AI servers now.
IR, specifically in servers with their Grace and Vera CPUs.
That's amazing, using a mobile memory type to solve a data center problem.
And this strategic adoption has triggered massive volatility across the entire DRAM market. The demand surge, driven by AI's insatiable need for power efficiency, has put unprecedented pressure on the LPDDR5X segment.
So memory manufacturers are scrambling.
They're scrambling to reallocate their manufacturing capacity toward HBM and this new AI server-grade LPDDR5X segment.
And the numbers reflecting this market shock are staggering.
They show the raw financial power of this AI demand. DRAM prices are already up around 50% year-to-date, fueled almost entirely by AI hardware investment.
And they're projected to rise even more.
Another 30% in the fourth quarter of 2025. This scarcity and rising price of conventional DRAM is a direct consequence of memory manufacturers prioritizing the higher margin, high-demand HBM and LPDDR5X segments for AI.
It's all connected.
All connected. Samsung, for instance, is projected to post its highest quarterly profit in 3 years, largely thanks to this massive AI-driven surge.
So beyond primary memory, AI's massive data appetite is also changing storage. We need storage that acts more like memory than a traditional hard drive.
That's absolutely right. Storage must deliver higher performance, and it needs to be located physically closer to the compute resource to minimize that data transfer time.
And the density is just exploding.
It is. We are seeing drives being announced this year, like Samsung's 128 TB E3S drives, with plans to launch monstrous 1 petabyte drives by 2028. But density alone doesn't solve the latency problem.
So if you can't bring the data to the compute fast enough,
You must bring the compute to the data.
and that's achieved through CXL memory solutions.
Right, or CXL-MEM, integrating a processing near memory, PNM engine. This means embedding specialized accelerator logic directly into the CXL memory controller.
So instead of moving massive data sets across the PCIe but to the CPU, you just do some of the work right there on the memory module.
Exactly. You perform simple tasks like filtering or basic search right near the memory. This fundamentally overcomes the traditional PCIe bottlenecks.
And for AI inference, which has very specific demanding requirements.
For inference, where you have repeated access to small, critical chunks of data, a new category called memory-attached storage, MAS, is emerging.
And its purpose is just raw speed.
Raw speed. MES is designed to sit as close as possible to the compute resource, outperforming conventional SSDs and delivering latency that begins to approach memory speed.
Finally, with all this data usage exploding, security has to be paramount, especially protecting data while it's actively being processed.
That's where confidential computing becomes critical. It requires a multi-layered security framework designed to protect data in use during the training and inference stages.
And this has to be built into the hardware itself.
It does. This involves implementing secure device identity, establishing secure communication channels, and creating secure processing environments known as trusted execution environments, or TEEs. This level of security cannot be achieved with software alone. It must be implemented at the silicon level.
Okay, that covers the physical constraints and breakthroughs in hardware and the software blueprints. Now let's pivot to the algorithmic challenge. How do we actually design the AI itself to maintain long-term context and learn continually without suffering from cognitive collapse?
This is the core problem. The current foundational limitation in large language models is their issue with context and continuous learning.
They're limited to their static training data or a finite input window.
Right, the amount of text they can hold in their immediate attention span. And if you push the model to learn new information, you inevitably run into a problem known as catastrophic forgetting.
Catastrophic forgetting sounds dramatic. What does it mean in practice?
It's highly technical, but the concept is simple. When the model learns new information, it adjusts its internal weights and parameters globally. These new adjustments often fundamentally sacrifice or degrade the model's proficiency on older, previously learned tasks.
So it essentially wipes its own slate clean to absorb new knowledge.
It does, which leads to this rapid proficiency loss on the old material. And that's a massive constraint for an agent that needs to learn continually in a real-world dynamic environment.
We can draw a parallel here to older network architectures like long short-term memory networks, LSTMs. They faced similar problems.
That's a crucial precedent to understand. LSTMs were the algorithmic solution designed to prevent the exploding or vanishing gradient problems in traditional recurrent neural networks.
And they did this by introducing a dedicated memory cell.
They did. This gave them the ability to store information over dozens or even hundreds of time steps, which finally allowed them to capture long-term dependencies, like remembering the subject of a sentence that began 2 paragraphs ago.
And how did LSTMs manage this memory cell without just filling it up with junk? That's where the concept of gates comes in.
Exactly. LSTMs are modeled after selective biological memory functions. They use 3 explicit gates to actively manage what goes in, what stays, and what's released.
Okay, what are the 3 gates?
First, the input gate decides what new information should be added. Second, and most critically, the forget gate acts as an active filter. It deletes irrelevant information by multiplying the signal by a value close to 0.
So it doesn't just forget by accident, it actively decides to forget something.
That's the key difference. And finally, the output gate controls what part of the current cell state, the synthesized memory, is passed out for the next step. LSTMs were proof that effective memory requires active, selective management.
So those principles of selective memory management are now being extended dramatically to modern large models with something called nested learning.
Yes, and nested learning, or NL, represents a major theoretical shift because it unifies architecture and optimization. It treats a single machine learning model as a system of interconnected, multi-level optimization problems.
And each of those problems has its own context flow and, critically, its own independent update rate.
That's the key. So it's no longer one giant brain that updates all at once. It's a collection of modules, some updating daily, some hourly, some weekly, all based on their specific function.
That's the perfect way to frame it.
And this perspective leads to the continuum memory system, CMS. Instead of a simple short-term versus long-term split, CMS views memory as a spectrum of specialized modules updating at different frequencies.
So a module handling low-level syntax might update very rarely,
while a module handling recent user interactions might update constantly. This creates a much richer, more effective memory system optimized for continual learning while inherently reducing the chance of that catastrophic global forgetting.
And we have a tangible proof of concept for this, right? The HOPE architecture.
Yes. The HOPE architecture was designed using these nested learning principles and augmented with these CMS blocks. It's a self-modifying, recurrent architecture, and experiments have shown its superior performance in language modeling tasks, and crucially, its excellent memory management in long context reasoning challenges.
Like the needle and haystack tests.
Exactly, where the model has to retrieve a tiny, critical piece of information buried deep within a massive text sequence. The CMS offers a demonstrably more efficient and robust way to handle these extended sequences without context collapse.
Okay, moving back to practical agents deployed today, like companion AIs or customer service bots, they're still plagued by this temporary amnesia when conversations get too long.
They are.
So what are the current state-of-the-art software solutions bridging this memory gap in the real world?
Well, the most common and effective technique used broadly today is retrieval augmented generation, or RAG-RAG. RAG fundamentally solves the problem of static knowledge. Instead of relying solely on the LLM's internal static training data, the AI augments its response by first pulling external knowledge and facts from high-speed vector databases, like FES or Pinecone.
So RAG ensures the agent is consistent and up-to-date by grounding the response in external vetted data.
Precisely. It provides consistency, it reduces hallucination, and it ensures the agent isn't talking about facts that are 6 months out of date.
And beyond RAG.
Beyond RAG, solutions are increasingly drawing inspiration from human cognitive psychology to manage the memory it already possesses.
How does human memory modeling help an AI?
We see methods called cognitive forgetting being deployed. These are inspired by models like the Ebbinghaus forgetting curve, which describes how we as humans progressively forget details over time unless a memory is actively reinforced.
So the AI uses decay functions to progressively eliminate less significant memories.
It does, while actively reinforcing data that's referred to often. This selective forgetting is essential to prevent information overload and keep the agent focused on what's relevant to his mission.
So if decay is external recall and cognitive forgetting is internal housekeeping, what's the final piece?
That would be behavioral memory. This tracks the user's engagement patterns. Which topics did they mention repeatedly? Which documents did they ignore? Which conversations did they return to?
By analyzing those patterns, the AI can prioritize and preserve what's most important to the user.
Exactly. This level of personalized memory is what allows agents to transition from being generic tools to feeling like highly personalized, relevant companions over time.
We've covered the staggering technical complexity required, the HBM breakthroughs, CXL elasticity, and nested learning to build these agents. Now we turn to the most critical topic, the human complexity.
Right.
What does this mature agentic AI mean for society, the labor market, and frankly, our own brains?
This is perhaps the most profound societal insight coming out of the recent research. If we look at the historical context, over the last century, technological change tended to follow a very clear pattern.
It favored jobs with higher education, more women, higher pay.
Exactly. Technology primarily replaced routine manual work on factory floors or routine cognitive work like clerical tasks.
But the core argument now is that this historic pattern is set to completely reverse.
That is the prediction. Generative AI is capable of performing non-routine cognitive tasks, particularly those that don't require decades of specialized judgment or deep tacit knowledge.
So if AI substitutes for these cognitive tasks, the next wave of job displacement might hit the exact jobs that benefited over the last 100 years.
Precisely. We're talking about high education, white-collar roles facing the most exposure, relatively speaking.
So think of the junior paralegal, the entry-level consultant, the financial analyst just out of university.
Exactly. The tasks they perform, drafting initial summaries, performing routine data audits, compiling background research, are heavily exposed to automation.
But the senior partner, or the CFO, whose jobs rely on nuanced judgment and client relationships, they're far safer.
Much safer.
But this carries an immense risk for young workers entering these fields. You risk eliminating the entire apprenticeship pipeline.
That's the critical long-term concern. Entry-level jobs are crucial, real-world training grounds where young workers acquire the tacit knowledge and judgment needed to become future managers.
And if AI automates those specific entry-level cognitive tasks,
It could potentially eliminate the entire first rung of the white-collar career ladder. And that leads to a long-term deficit of experienced human talent and just exacerbates inequality.
and we are already seeing this reflected in corporate strategy.
Absolutely. AI usage in the U.S. workplace has nearly doubled in just 2 years, reaching a 67% adoption rate. And we are seeing executives publicly warning that AI will trigger deep cuts in highly standardized white-collar roles,
Particularly in areas like administration, HR processing, and routine corporate finance.
confirming that this disruption is already underway and moving much faster than previous automation waves.
Beyond economics, we need to address the human cognitive impact. There's research from the MIT Media Lab warning that an excessive reliance on AI may actively contribute to the shrinking of our critical thinking abilities.
This boils down to the crutch versus tool dilemma. If you use AI simply to do the work for you, you're just taking a cognitive shortcut.
Like relying on an AI to write the first draft of a complex report.
Right. That prevents you from engaging in the difficult, necessary mental struggle that generates true, novel conceptual thought. As experts note, the assignment output is just a vehicle through which learning occurs. If AI delivers the output, the learning process is bypassed.
But wait, if AI can handle the routine, non-critical cognitive tasks, the 80% that is often repetitive, doesn't that free up human capacity for higher-level strategic work? Isn't that the whole point?
That is the theoretical promise, and it's the ideal usage model. The danger lies in our human tendency toward inertia. If we use the AI to save effort instead of shifting that saved time toward more complex thinking, then we atrophy.
So the key difference lies in what the human brings to the collaboration.
Right. And what the human brings, the irreplaceable core advantage, is judgment.
Judgment.
Exactly. While machines excel at statistical calculation, humans are, as some say, better than Bayesian. We possess intuition, moral reasoning, and the ability to detect subtle distinctions that drive conceptual change. Qualities machines fundamentally lack today.
So if AI produces endless amounts of high-quality content and information, what becomes the most crucial, monetizable human skill?
It shifts entirely to discernment, evaluation, judgment, and reflection. Since AI output is often incredibly convincing, it can sound totally authoritative, but is sometimes profoundly wrong. The proliferation of cheap intelligence means the ability to verify, question, and apply ethical human judgment to the machine's output is more critical than any technical skill.
It's the skill that cannot be outsourced.
Not yet, anyway, and it requires constant cultivation.
Finally, let's address the rapidly emerging ethical and regulatory landscape. The dark side of generative AI is already having a tangible impact.
It is. Malicious actors are already fully exploiting its capabilities to create high-accuracy deepfake media. For example, realistic yet entirely fabricated racist propaganda videos.
Designed to stoke social divisions and spread misinformation at scale.
And it bypasses traditional media literacy defenses. This requires urgent investment in watermarking technology and rapid media verification tools.
And the high-stakes issue of liability is front and center as these agents move into customer-facing roles.
Absolutely. We are seeing landmark cases that challenge the legal definition of responsibility. The Colorado lawsuit linking an AI chatbot to a teenager's suicide raises profound questions about liability for autonomous systems interacting with vulnerable users.
Who is responsible when an AI provides harmful advice or it makes a faulty decision that leads to real-world harm?
That's the question the courts are going to have to grapple with.
And we see similar issues in commerce regarding opaque decision-making.
Yes. Amazon's Help Me Decide shopping agent has sparked consumer backlash. The concern is the opaque nature of its decision-making. Users don't know why it recommended one product over another,
Raising major concerns about how their personal data is being leveraged.
in a completely non-transparent manner.
We're also seeing creative conflict emerge very quickly as AI is positioned as a direct replacement for skilled workers.
The creative sector is fighting hard against this. The emergence of the AI-generated actress Tilly Norwood, which agents are reportedly trying to sign for roles, has caused outrage.
Union groups like SAG-AFTRA see this as a dystopian first step toward mass replacement of human actors.
And similarly, Channel 4 in the UK debuted its first AI news presenter, sparking clear job displacement concerns across broadcasting and the creative industries.
So globally, how are governments responding to this explosion of autonomous capability?
The response is fractured. In the U.S., states are moving ahead with a confusing and potentially contradictory patchwork of AI legislation.
Which creates compliance challenges for national companies.
Massive challenges. And it's versus the unified international approach we see from other blocs.
Like the BRICS nations.
Correct. The BRICS nations are pushing for UN-led global AI governance. Their argument is centered on equity. They argue that current AI norms are dominated by Western tech giants, and there needs to be broader, internationally agreed-upon standards.
To ensure equitable access and ethical oversight that reflects global values.
Not just Western commercial interests.
So what does this all mean? If we zoom out, we are seeing a massive acceleration driven by this shift from generative AI to truly autonomous agentic AI.
Right. Systems that plan and execute without constant human intervention.
And this means that while the software stack is consolidating around known reliable anchors, Python, LangChain, OpenAI, the underlying hardware is under immense historic pressure.
Absolutely. The pursuit of autonomy demands radical solutions to power and speed, leading to these pivotal, non-glamorous breakthroughs like hybrid copper bonding in HBM or the strategic use of mobile LPDDR5X in servers.
And critically, the algorithms themselves are finally catching up to the hardware.
They are. The breakthroughs in the algorithmic domain, particularly the nested learning paradigm with its continuum memory system, show that AI progress isn't just about writing better code or training bigger models.
It's fundamentally about solving the physics and engineering constraints of processing and memory.
And these solutions are what enable systems to learn continually and effectively manage their context over time, making them truly autonomous.
And as we close, the long-term impact on our human workforce is the one that requires our immediate strategic attention.
It is. If the historical trend of technological change is set to reverse disrupting the white-collar educated workforce by automating those entry-level cognitive tasks, the stakes are raised immensely.
If the most crucial human skill remaining is the judgment required to verify AI's output and provide that ethical, moral context,
then we all have to ask ourselves a pretty serious question.
if the economic value of information is plummeting and the value of judgment is soaring, how will you ensure your time is spent developing that irreplaceable human capacity for critical reflection and discernment, rather than simply using AI as a cognitive crutch to avoid the difficult mental work you should be mastering? That is a question worth exploring deeply on your own.